TamTech Academy channel. Today we are going to solve some technical quiz related to thermodynamics, physical properties, fluid mechanics, compression, also pumps, and etc. So my recommendation to you, just stop in each problem statement to read it yourself and solve first yourself, and then continue to look the solution of the problem. So starting with the first problem, and we will read the problem statement and solve the problem with you, and then check our student solution in order to see if she is correct or not. The first question is, iron is a gray metal that has high density. It can react with oxygen to form rust and is attracted to magnets. How many physical and chemical properties are mentioned? As you know, physical properties describe what a substance is like without changing its chemical composition, but chemical properties describe how it reacts with other substances. Reactivity, acidity, these are all chemical properties, but shape, color, like melting point, etc., they are physical properties. For iron, being gray, which represents its color, density, also being attracted to magnets are physical properties. They have three physical properties. But reacting with oxygen in order to form rust is a chemical process, because we form new substance. So we have three physical property and one chemical property. At the end, I will check the solution of student. The second problem is, which statement best explains why corrosion is a chemical property? Firstly, we should know that corrosion is a chemical property because it changed metal into new substance, as I mentioned in our previous problem. For example, iron reacts with oxygen to form what? Rust. Physical change, but like color and shape, doesn't create new substance. But corrosion does. That's why forming a new substance here should be a key idea. It results in the formation of new substance. Yes. And third one, why is melting point classified as physical property even though heat is applied? Okay, corrosion. Okay, melting point is physical property because even though heat is applied to melt substance, it doesn't create new substance. Okay, it just, we give heat to change solid into liquid, but it's still the same material. For example, water as a ice, water as liquid, or water as vapor. That's why we call it as physical property. And the answer should be because no new substance is formed. Okay, moving to fourth question. Actually, it's like problem. We should solve it. Okay, first read the problem statement together. So it said that a garden hose attached with a nozzle is used to fill a 10-gallon bucket. The internal diameter of hose is 2 cm and it's reduced to 0.8 cm at the nozzle exit. If it takes 50 seconds to fill the bucket with water, determine the hose and the average, determine the volumetric and flow rates of water through the hose, and also the average velocity of water at the nozzle exit. So we have, this is the picture of the, by the way, problem. So we have two parts. First, we need to find volumetric and mass flow rate, and then the average velocity. Okay, let's go. The volumetric flow rate will be found like this. We will divide volume to delta T. It will give us volumetric flow rate. Our volume is 10 gallon. Our delta T is 50 seconds. We need to convert gallon to liter or meter cube, whatever you want. We know that in order to cancel out, we should put like this. They are canceling out, and 1 gallon is equal to 3.6 liter. You don't need to remember it, just you can search it from internet, and it will give us 0.757 liter per second. Liter per second. And in order to find mass flow rate, we need to multiply our density to volumetric flow rate. And it will be like our density. You can write it with kilogram like this, 1 kilogram per liter, or you can write 100 kilogram per meter cube, but you need to convert it also meter cube in order to write them in unit, in same unit, and multiply 0.757 liter per second will give us 0.0757 kilogram per second. Okay, first part is done, and in the second part, it say that the average velocity of water. In order to find average velocity, we will use this equation Q, or you can denominate it as V is equal A multiplied by U, which comes from continuity equation, as I said multiple times. A is equal to P d square 4 multiplied by U. We first need to find cross-sectional area. We know P is 3.14 multiply D, it's required that the average velocity of water at nozzle exit. As it is said, it's exit. That's why we will take diameter as 0.8 centimeter. 0.8 square divided by 4. It will give us 0.5 approximately centimeter square, but you can convert it to meter square also, and we will actually. And Q again, we need to find U. U is equal volumetric flow rate divided by A, which is cross-sectional area. This is 0.757 liter per second, and A is equal 0.5 0.727 multiply 10 to the power of minus 4 meter cube. As you can see, I converted it to here cubic meter. That's why for liter, I also convert it to meter cube. 1 liter is equal to 10 to the power of minus 3 cubic meter, and they will cancel each other and will give us 15.1 meter per second. Okay, and moving to fifth question, we have multi-stage compression, and they ask that why is multi-stage compression with intercooling preferred? Okay, let's open our solution also, our student solution actually. Okay, why is multi-stage compression with intercooling preferred over single-stage compression in industrial application? Discuss from both thermodynamic and mechanical point of view. Draw a PV diagram, draw process flow diagram also. So, okay, in industry, firstly, I would say that we prefer multi-stage compression with intercooling because it reduces the work needed to compare to a single-stage compression. I will draw a PV diagram and explain it clearly, but thermodynamically cooling between stages lower the average temperature. Also, it will reduce energy consumption. Also, mechanically lower temperature will reduce temperature on compressor component, and it will increase the equipment lifetime. And it's written here correctly. Well done to our student. And also coming to PV diagram, it's a little bit inaccurate here. That's why I will draw it by myself. Just a minute. So here we have isothermal curve, we have adiabatic curve. So if we use multi-stage compression, it should be like this. Like we are starting here, we have intercooler here. That's why it will go like this. It will go like this. It will go like this. It will depend the number of stages. So the area under PV will give us the work done. So you see, actually, the red is less than the green one. That's why we actually save the work here. That's why multi-stage compression is preferable. You can explain it in PV diagram also. Coming to PFD, here it's drawn wrongly because in each stage of compressor, we need to put intercooler and knockout flash drum, which is correctly drawn here. We have compression, then we put it to intercooler here in order to reduce temperature. And after that, if we reduce temperature, there is a possibility to have two phase, and that's why we put knockout drum or flash drum, whatever you want to say. It's just simple separation process based on density of fluid. Like gas will move to the top, but liquid will move to the down, and separation will occur. After that, from the top part, we again put compressor, again the same process. We put intercooler, again knockout drum, and this will represent only one stage. If you put again in sequence like this, in here it will be second stage compression, then third stage compression. Here I ask 3-stage compression, and that's why you need to draw it like in a like third time, like the same process. Okay, and the third part, draw the complete cycle and explain in detail the physical mechanism of surge and stone wall. Okay, in compressor, we have two type of operational issue that you should remember. First one is surge. Surge occurs when the compressor is forced to operate at low flow rate, and it will cause flow reversal and oscillation in the process. But stone wall, in other words, choke, occurs at very high flow rate and in a really sonic speed. They both are critical limit, and that's why we need to operate in the like region. Here you can see also the graph for it. We have surge issue, we have stone wall issue, and we need to operate in region. So third part, and it's written correctly here, and draw the complete cycle and interpret it in a cycle of, on a PV diagram for Rankine and Carnot cycle. Okay. This is a full cycle. Full cycle actually consists boiler where heat is given to boiler, then turbine where heat extracted from turbine, and we have condenser where heat again removed from condenser, and pump where work is given to the pump. This is full cycle, and we should represent it in PV diagram for Carnot and Rankine cycle. In Carnot cycle, we have two isothermal and two adiabatic processes. As you can see from here, from 1 to the 2 is isothermal expansion, from 2 to the 3 is adiabatic process, and from 3 4 4 isothermal again compression, and from 4 to 1 again adiabatic process. And you know, Carnot cycle is considered as perfect cycle. Here, like heat is absorbed during heat isothermal expansion. Work is done again during adiabatic expansion, but heat is rejected during isothermal compression, and adiabatic compression also restores the system. Coming to Rankine cycle, here you can see the curve. We will have two isothermal. From 1 to the 2 is isothermal expansion. From 3 to 4 is isothermal compression process. From 2 to the 3 is adiabatic, but from 4 to the 1 called isochoric process. So overall, here you can see like 4 steps, but 3 different processes: isothermal, adiabatic, and also isochoric processes. As it's written here correctly, it's used for steam turbines, convert heat into mechanical energy. The efficiency for Rankine cycle will definitely less than Carnot cycle. So if you want to learn more about cycles, you can write like comment below or drop your question. We will answer them, or we will like record new video for cycles also. So we finished this with this question. Moving to sixth question. Explain the difference between MPSH available and MPSH required. Why it's critical for pump operation. We actually talked already MPSH available and MPSH required. MPSH, what's MPSH? It's net positive suction head, but what's available? MPSH available is the pressure the system actually provides at the pump suction. Sorry, and MPSH required, however, is the minimum pressure that the pump needs to avoid cavitation. MPSH required is given by vendor, but MPSH available is calculated by process engineers. As I mentioned, MPSH available should be larger than MPSH required. Describe the main issues with pump. What are typical signs and how does it damage pump components? How to prevent this issue? Okay, there are several problems in pump operation, but the main one is cavitation and vibration. Signs for it are noise, reduced flow, fluctuating pressure, and also vibration. These issues will cause damage to pump internals like impeller, seal, bearing, and etc. In order to prevent this, we have different type of solution. You can increase MPSH margin, correct pump selection, because it's important whether you choose like for example centrifugal pump, whether you choose PD pump, or etc. Regular maintenance and also controlling the fluid temperature and viscosity is important. But besides, coming to MPSH available equation, you can see from here that MPSH available is equal to suction side pressure divided by rho g plus elevation minus pressure loss divided by rho g and minus vapor pressure divided by rho g. From the equation, you can see that suction we can like increase suction pressure. Also, coming to like again besides that, we can minimize bend and fitting because we have pressure loss here. Also select larger diameter, lower the liquid temperature, and etc. But coming to PF, which represents our pressure loss, we have 8 factors that need to that affect our head loss, and you need to know them by heart. First one is flow rate. As it's seen from the equation, you increase flow rate, it means that velocity at the same time will increase. If the velocity increase, head loss will increase. That's why automatically MPH available will decrease. Second one, diameter. If you increase the diameter of the pipe, as it's inversely proportional with velocity, velocity will decrease and head loss will decrease also. But MPH available will increase. Third one is roughness of the pipe, also corrosion and scale. They also affect because, for example, if you have corrosion, it means that diameter of pipe will decrease. If diameter of pipe decrease, velocity will increase. That's why head loss will also at the end increase. Besides, viscosity of liquid also important, length of pipe, fittings, elbows, etc. Also straightness of pipe. These all affect our PF at the end and passage available. Okay. Next part is, as an engineer, you decide to use a centrifugal pump to handle a highly viscous fluid. After several months of operation, performance problems occur. What do you think could be the cause of the problem? Why did it occur? How could it have been prevented? Okay. Actually, we know that centrifugal pumps are designed for low viscosity fluid. That's why if we have highly viscous fluid, this will automatically lower our flow, will require higher energy, and possible overheating will cause. But in order to prevent this, we can use a positive displacement pump instead of centrifugal pump, or even we can increase temperature in order to decrease the viscosity of the fluid. Okay, moving to the next question. In the 7th question, we have 3 types of process: isothermal, polytropic, and adiabatic. In adiabatic process, overall, we know that no heat is exchanged with surrounding. So when the gas is compressed, all energy inside stays in the system. That's why the temperature and pressure increase more rapidly. As you can see from the graph, it represents with A, which is steepest in the PV diagram. Coming to polytropic process, the system may exchange some heat with surrounding. Actually, it occurs. Because of this, partial heat transfer will occur and the pressure change moderately as we change volume. Therefore, it will lie between adiabatic and isothermal curve on PV diagram. Coming to isothermal process, as you know, in isothermal process, the temperature remains constant. As the gas is compressed, heat flows out the system to keep temperature actually unchanged. Because the heat leaves the system, the pressure increases more slowly, however, making it the flattest in PV diagram, which is C. Its next question. Any thermodynamic process is said to be spontaneous in the forward direction if, so okay, here we have system entropy, here we have surrounding entropy and total entropy. Even we have and system entropy, if even system entropy decreases, it doesn't mean that total entropy will decrease or increase, because here what matters is the overall universe. Sometimes the system becomes more ordered, but the surrounding gain even more entropy. As long as our total entropy increases, the process will be spontaneous. That's why delta S total should be higher than 0. Next question, select the correct answer. We have a reaction. A student is investigating the feasibility of producing NO2 at 400 Kelvin using the reaction represented above. To better understand the reaction, the student looks up the following thermodynamic data in reference text. Enthalpy change and also entropy change. Based on the data, is the reaction thermodynamically favored at 400 Kelvin? Assume that both parameters are independent of temperature. Okay. For this, we need to write our equation. Delta G, which is Gibbs free energy equation, is equal to delta H minus E delta S. The point here is that you should keep in mind that converting unit one to the another to make it the same. here you see that delta H is given by kilojoule, but delta S is given by joule. That's why you need either convert kilojoule to joule or joule to kilojoule. So delta G is equal, delta H is minus 120 minus temperature is 400 Kelvin and multiply by delta S. Delta S is minus 150 divided by 1000. I converted it to kilojoule. And when I calculate it, it will give me minus 60 kilojoule per mole. As delta G is negative, it means that the reaction is thermodynamically favored. Okay, yes, because delta G is less than 0. 10. When a gas is compressed isothermally at a temperature below its critical temperature during the phase transition, which of the following best describes the behavior of the pressure as the volume decreases? Okay, when we decrease the when we compress gas isothermally below its critical temperature, it can condense into liquid also. This is also possible. And during this phase transition, gas and liquid coexist. As the gas continues to compress, more gas will turn into liquid. But pressure doesn't change. If you ask why, because you supply more pressure, but it will be its saturation pressure. And extra compression only change the proportion of the liquid and the vapor. Therefore, pressure remains constant while both exist, like both phase, liquid and vapor exist. Okay, very last question. This is problem. We need to read it and solve. I will open the solution of my student. Okay, here you can see that water, all parameters. I will ask from you, just read them and then look the solution of the problem. We have, they ask find the major and minor head loss, pressure drop, and pumping power requirement. Okay, I will first find major loss and then minor loss, then pressure drop, and then pumping power. Okay, let's go. We calculate major loss. I will take my pen. We calculate major loss like this. H is equal to F multiply L divided by D multiply U squared divided by 2G. This is major loss equation. Okay, here we need to find what F because we don't know F, which is friction factor. I showed it in our pump design video that how we find friction factor. First, we need to find Reynolds number, which is equal rho UD divided by mu, and it's as it's seen from here that it's laminar flow. If it's laminar flow, we even don't need to find it from chart. We have equation F is equal to 64 divided by Reynolds, and it will be like 0.0365. After finding F, we just put it here, and find that our H major will be approximately 4.6 meter. Coming to minor losses can be calculated with two method, with loss velocity method or equivalent length method. Here we have fitting, bending, etc. That's why we can use whatever you want to find our minor losses. But if it's interesting to you, just drop your question below. We will explain difference between loss velocity method and equivalent length method. Here we will use loss velocity method. And for loss velocity method, the equation will be k u squared divided by 2g. In order to find k loss velocity constant, we need to calculate sum all k. I will show you one table. Here you can see k values. We have what? We have sudden entrance inlet. It means that we have tank inlet, sudden expansion. It's equal to 1. We have a fully open globe valve. Okay, fully open globe valve, which is 6. We have two standard 90-degree elbow, which is this. You can take what number you want from this range. And we have sudden exit, tank outlet here. You just sum this one, this one, this one, and this one. But you need to keep in mind that we have two standard elbow. That's why you need to multiply this one. Okay, move to solution. Okay, 0.6 multiplied by 2 plus 6, but it's not correct because she didn't consider the inlet and the outlet part. It will be plus 1 plus 0.5, and it will give me 8.7. After finding K total, we will find H minor. Here we will write, instead of this 8.7 and calculate it, it will give us 0.36 meters. And then we will sum them in order to find total head loss. I will write here H total is equal summation of 0.36 and 4 point approximately, if I'm not mistaken, yeah, 4.6, yes. H total will be 4.96 meter, and PF is equal rho GHF. And here we know rho is 1000, G is 9.81, and HF, which we found already, and PF will be Pascal. You can convert it to Pascal also. This is not correct, as you can see from there. Then we need to find pumping power. Pumping power, how we find it? Pumping power is equal P multiplied by flow rate. We know that from continuing the equation, Q is equal to U multiplied by A or U multiplied by P d squared 4. We know that U is 0.9 multiply P multiply D is 0.003 squared divided by 4. And this is the number of Q. For power, we need to multiply pressure, which is equal to this number, with Q, with this number, multiply this number, and it will give us 0.3 watt at the end. Yeah, this part is not correct. Overall, we solved all questions from this technical question. Let's look the solution of our student. Yeah, this is correct. This is correct. This is also correct. Yeah, we checked it. It's correct. It's correct, but there is have a little bit inaccuracy in diagram. This is also correct. This is correct. This is correct, and this is correct. But this is, yeah, this is again, this is not correct. It should be variant, and like problem itself, a little bit we have difference in finding K. That's why there is mistake. Overall, we finished all technical quiz part. Thank you for listening and watching our video. See you next videos.